Hello everyone, I'm Sandor Bergi from the University of Bristol, and I'm going to talk about the robust tracking of periodic solutions in experiments with control-based continuation. This research is motivated by the concept of digital twins, which is an increasingly more popular modeling approach these days. Digital twins are essentially data-driven virtual counterparts of physical structures, which can be used either as an aid in the design phase or help with operational, management, or maintenance decisions. Our study focuses on the data acquisition part, which may be challenging for a number of reasons. For instance, if we have a considerable amount of process noise in the system, that can lead to a loss of information about some features of the underlying system dynamics, or in case of nonlinear systems, it's quite common to have unstable steady-state solutions of the system, which are also difficult to get information about. Therefore, the question what we ask ourselves is how we can extract more information from the physical system, which would allow us to build better and more representative models or digital twins. Control-based continuation is one such technique that's capable to extract more information about nonlinear dynamical systems with periodic orbits, as it would be possible with the standard open-loop measurement approach. The reason for that is basically that control-based continuation is capable to trace not just the stable but also the unstable periodic solutions in the system. The examples I'm going to show are going to be force vibrations, but the method itself can be actually generalized for autonomous systems and self-excited vibrations as well. The objective of our study is basically to assess the control-based continuation techniques' robustness against process noise in the system, and we would like to compare it against open-loop solutions. Then, in the second part of my talk, I'm going to speak about another application of the control-based continuation technique, or at least some idea of it, and how it can be used for hybrid, or as it's called otherwise, hybrid-in-the-loop testing of a three-star structure. Our experimental rig with the nonlinear physical oscillator, which we used to test the control-based continuation algorithm, can be seen on the photo and the schematics in the left-hand side of my slide. And the schematic also shows the separate parts of this device. The oscillator itself consists of a cantilever beam which has a tip mass at the end, and to this tip mass there are a number of permanent magnets attached. These magnets are facing an electromagnetic coil that's mounted in the stator part of the device, and this coil can be also used to pollute the system with process noise artificially, so we can test our algorithm at different noise levels. Eventually, the interaction of the structural, the inertial, the electric, and the magnetic effects result in a nonlinear restoring force in the system. Therefore, its dynamics is similar to a Duffing oscillator. Therefore, if we carry out an open-loop frequency sweep at a relatively low noise level, we can experience a different response when we are increasing and decreasing the forcing frequency, creating a hysteresis loop. The frequency range where this hysteresis loop is located is commonly referred to as a bistable parameter domain, because in this frequency domain, for one set of parameters, the system has two coexisting steady-state periodic solutions. Actually, there is a third periodic orbit as well. However, this is unstable, therefore it's practically undetectable in the open-loop measurement approach. Now, if we do the same test at a higher noise level, then basically we begin to lose information about this bistable parameter range. We may be still aware of its presence because we may experience some jumping between the domains of attractions of the two stable solutions. Nevertheless, this picture doesn't give too much information about the boundaries of the bistable parameter domain. Right, so let's do something else, and this slide is going to explain the basic steps for control-based continuation algorithm. Right, so let's imagine that we already identified a number of periodic solutions in the system, and then in order to find the next solution in this range, the first thing we do is that in our control law, we increase the fundamental harmonic components in our control target. Now, if we have a stabilizing control law, then our system is going to settle at a steady state. However, this not necessarily will be at the solution branch corresponding to the open loop system. Therefore, we apply an iterative technique which corrects the forcing amplitude and the higher harmonics in the control target to find this solution marked by yellow, which is also a periodic solution in the open loop system. If we trace the response at different forcing frequencies and different forcing amplitudes in the open loop and the control-based continuation approaches, then the first thing that we can see that of course we have more information about the system, because we have not just the stable but also the unstable steady state solutions with the control-based continuation. However, that's also visible that the presence of the control actually already results in a much smoother surface than what we obtain with the open loop frequency sweeps, even though this was carried out at a relatively low noise level without additional noise in the system. This is even more visible if we compare the performance of the control-based continuation and the open loop approaches at identifying a Duffing oscillator model from the response collected at a constant frequency for varying forcing amplitude. So as you can see, if we don't add any additional noise to the system, then basically the two identified curves, the red corresponding to control-based continuation and the blue one corresponding to the open loop parameter sweep, are essentially identical. However, as we start increasing the noise level in the system, then what we see that we begin to lose information about the exact boundaries of the bistable parameter range in the open loop approach, whereas control-based continuation is still reasonably robust in retaining the original response, even at relatively higher noise levels. Right, so let's move on to our next example, which is a hybrid testing of a three-story building. By hybrid testing, I mean an experiment when part of the structure is simulated, as it is in interaction with the physical substructure through a number of sensors and actuators. Now, realizing such experiments is usually quite challenging, as the presence of the actuator actually contributes to the system dynamics in quite a significant way, which can lead to fidelity or stability issues with the system. Now, the traditional way to address these challenges is usually applying a control or using an inverse model of the actuator. Now, instead of that, we are going to propose a control-free iterative method that's originated in our control-based continuation technique. But before that, let's have a look at how our experimental setup actually looks like. We consider the two top stories of the three-story structure as the physical substructure system, which is connected to a virtual bottom story. So actually our true assembly, which can be seen on the right-hand side, consists of three stories, composed by the two top stories of the physical structure and the virtual story at the bottom. The actual physical story, along with the shaker and the real-time controller device, is going to be considered as the interface of the experiment. So what we would like to do basically is to measure the force at the interface and the physical structure, and feed that force to the virtual substructure, and use this information to simulate the displacement, and then feed that displacement back to the physical substructure by using some method which makes the virtual and the physical bottom stories move synchronously. Now, just to highlight how complicated this task is, I carried out a stability analysis where I modeled the contribution of the actuator dynamics to the system as a time delay, resulting in a delay differential equation. If we calculate the stability chart of the trivial equilibrium in this system, then what we find that basically the maximum tolerable time delay is quite low, so it's only 100th of a second. But even if we were in the relatively limited stable parameter range, we would even find a different response of the system than what we would expect from the true assembly. Therefore, this direct and quite naive approach is not really effective for hybrid testing. So as I mentioned in the beginning, the traditional way to address this issue is either a control or an inverse model of the actuator. However, instead of that, we propose an iterative technique which works at least for periodic forcing. Of course, this is somewhat limited, but already covers the most common testing scenarios in engineering. So what we actually do is that we break the feedback loop between the virtual and physical substructures, and instead of feeding back the displacement of the virtual substructure to the physical one directly, we use an iterative technique which finds the appropriate amplitude and phase for the signal sent to the shaker, which eventually results in a synchronous motion between the virtual and the physical substructure. By doing so, basically, we eliminate any sort of instabilities which would have been related to the feedback or the control. And this method doesn't require any inverse model of the actuators either. Therefore, it's not just more stable, but also easier to implement. And our early experiments indicate that actually this method is capable to trace the frequency response of this hybrid experimental setup. So to summarize my talk, in the first part I was speaking about the control-based continuation algorithm, which is a method to trace periodic solutions in nonlinear experimental systems. This method was found reasonably robust against process noise in the system, and we can conclude that basically for this reason it's much better in extracting the finer details of the system dynamics than it would be possible with the more standard open loop approaches. And also the idea of this iterative measurement approach could be effectively used for the hybrid testing, as I showed it on the example of the free-series structure. I also would like to highlight one of our journal papers that's recently been published in Nonlinear Dynamics, and with that I would like to say thank you very much for your attention.